Alrighty, so section 16.2 is really an extension of what we did in section 16.1, and we really focus on that specific heat formula, which remember was Q equals MC delta T. Now we add a little bit of business to this, and that business is this idea of a calorimeter. So Q equals MC delta heat, or specific heat. It's a really good formula, but we need a way that we can measure that specific heat of each and every substance, okay? A calorimeter is an insulated measuring device used to measure the amount of heat absorbed or released in a chemical reaction. Now, in a calorimeter, it's going to have two parts. It's going to have essentially a cup with water, and then you're going to have the part that actually has the chemical reaction occurring in it. Because there's both water and a chemical reaction that is occurring, we have to take both of those things into consideration as we go through and we perform some calculations. So in our calorimetry, if I were to say, hey, find this specific heat of this metal, what you would do is you would heat the metal up. Okay, you get that metal up to a really high temperature. You would record what temperature you heated that metal up to, and then you place the metal into your calorimeter. And you can see from the slide here, a calorimeter can be something as simple as two styrofoam cups nested together. So you put that really hot metal object that you know the temperature, and you place it into that water. Now, as you heated it up, that heated metal is going to transfer its heat from itself to that water. We are also measuring that temperature of that water, and so we can determine how much heat did our water gain. Now, in this scenario, water gained heat, so that means the metal must lose heat. That's an important concept to keep in mind as we go through and perform some of these calculations. So if we go to our next example here, it says a piece of metal with a mass of 4.68 grams absorbs 256 joules of heat when its temperature increases by 182 degrees Celsius. We want to know what is the specific heat, and we want to know, hey, could this metal be one of these metals listed in these tables? So again, just like we did in last section, what we're going to do is this. We are going to use our specific heat formula, which is Q equals M times C times delta T. Now, remember what we like to do. We like to list out our variables and identify what we have and don't have. And so our Q in this case is our particular heat that is either absorbed or released. Okay? So if we take a look here, it says, and I'm going to circle quite a bit here, this object or this metal absorbs 256 joules of heat. So I'm going to write down 256 joules, and then I'm going to ask you this. Okay, we are absorbing heat, so we are gaining heat. In other words, that means we need a positive sign in front of that 256. Now, our mass of our metal is simply just the mass in grams, and so we get this given at 4.68 grams. And then our C, well, we're finding that specific heat, so our C is a question mark. And then our delta T, remember, is the change in temperature. And so in this case here, our change in temperature, we don't have to worry about final minus initial because they said the temperature increases by 182 degrees Celsius. So our temperature increase is an increase of 182 degrees Celsius. So we go ahead, we plug our delta T in for 182 degrees Celsius, And now we can go and we can solve for C. So we're going to start out with our positive 256 joules. This is equal to 4.68 grams times our C, which we don't know, times our temperature change, which is 182 degrees Celsius. So I always ask, hey, how do we get this C by itself? Well, it's attached via multiplication, so we need to divide by everything it's attached to. And so we're going to divide on each side by 4.68 grams times 182 degrees Celsius. And then the next thing I'm going to say is this, all right? I have two items on the bottom here. And so what I need to do is this. I need to make sure there is a set of parentheses when I go through this division process. So in my calculator, I'm going to take 256. I'm going to divide it by parenthesis 4.68 times our 182. In parentheses, I press enter, and I get a value of 3 decimals for my C to be 0.301 joules per gram degree Celsius. Now, the second part of this question says, hey, what particular metal could this be? Well, check this out. On that bottom table, strontium has a specific heat of 0.301, so this metal could be identified as strontium. Okay, so we'll get a little bit more complicated here with some extra problems. But this will serve as a basis for our calorimetry examples, okay? So we'll keep moving on in this particular section. We move on to our next item of discussion here, and that is talking about, okay, thermochemistry and breaking it down to the specific parts. So in thermochemistry, we got to be concerned about 3 parts: the system, the surroundings, and the universe, okay? The system is the specific part that you are studying. So in that last example, that heated metal was the system because that's what we are studying. The surroundings is everything that is not the system. Okay, so the surroundings would be the outdoor environment. It would be the atmosphere. Everything else in the universe that is not the specific system. And then the universe here is both the system and surroundings. Okay? So we have to determine a lot about what heat does. Does it flow in or out of the system? If heat flows out of a system, it's exothermic. If heat flows into a system, it is endothermic. Signs are going to become a very important process here in a couple of slides. Okay, so remember the terms endo and exothermic, right? Then we talk about enthalpy. Now, enthalpy here, if we jump down to number 3, is defined as the heat content of a system at, very, very important here, at constant pressure. For us in this class, we're going to consider enthalpy to be the heat constant or the heat change of a system, okay? Now, the other thing is this. Down here at the bottom in red, it says delta H of your reaction is equal to the delta H of the products minus the delta H of the reactants. What this is saying is this. First off, H is representing our enthalpy, okay? And maybe I should have put that up here. That enthalpy is represented by the symbol H, okay? So enthalpy has the symbol H. And so down here on the bottom where it says delta H, that means change of enthalpy for the entire reaction is equal to the change of enthalpy, or H, of our products minus reactants. Okay? This is going to come into play in a couple of sections when we talk about some standard enthalpy of reactions and some values that we have to look up. But I want you to know this, okay? Enthalpy is the heat content of our system. Does heat flow into or out of our system? And we can determine that enthalpy with that calorimeter. Does heat go into a system or does it come out of the system? All right, so let's keep moving on here and let's talk about our final item for this section, okay? Our final item for this section is this. We just got done talking about endo and exothermic, and I said, hey, these things are going to come back into play. Here we go. We're going to tie enthalpy with our endo and exothermic. A negative delta H means two things. Number one, your enthalpy of your products is less than your enthalpy of your reactants. This means heat is lost or given off by the system. Because heat is given off by the system, it is an exothermic reaction. Now, on the flip side, a positive delta H of that reaction means the enthalpy of the products, the heat change of the products are greater than the heat change of the reactants. Heat is gained by the system, and we refer to that as an endothermic reaction. Okay, so it's starting to get really, really important that you understand terms and their associated signs and what that means that is happening to that chemical reaction or that specific system. Now, another thing to talk about, enthalpy, change of enthalpy occurs at constant pressure. We can find the heat change, Q, remember, Q equals MC delta T, if we are considered to be at constant pressure. Now, in our class, we will always utilize constant pressure, okay? What we'll do here in the next few class periods is we'll get a little bit more in depth into our calorimetry problems. We'll add a little bit more complexity to that calculation of Q equals MC delta T, and we'll tie that business of endo and exothermic to everything we learn in a calorimetry problem.